Kourou, June 1996, 12:34. ESA's prestigious, newly built Ariane 5 rocket was ready for launch after a delay of 1 hour due to bad weather. T plus 0 seconds. The cryogenic engine starts ignition normally. T plus 7 seconds. Successful liftoff from the station. T plus 37 seconds. At a height of 3700 meter, booster and main engine nozzle swivels. This makes the rocket veer off the course. T plus 38 seconds. With an attacking angle of more than 20 degrees, rocket boosters start disintegrating due to enormous aerodynamic loads. T plus 39 seconds. Due to disintegration, automatic distance sequence is initiated. T plus 40 seconds. Rocket and its payload worth over $1 billion is destroyed in under a minute. Every year, dozens of rocket launches fail by varying factors, and the year 1996 was not that different. But in case of Ariane 501, it was different. So, how did this happen? Further, we need to peek a bit at its history. You see, European Space Agency had been using Ariane series rockets for a long time. Ariane 4 was one of its very successful launch vehicles. All the rockets from Ariane 1 to 4 shared the same basic design and were underpowered to perform heavy payload operations. So in the year 1986, ESA decided to develop a more powerful launcher with a new design, and thus Ariane 5 was born. But a bit late and also very costly. The whole Ariane 5 program cost around $8 billion at the time, $15 billion in today's terms adjusted for inflation. Also, the development of first launcher took nearly a decade. With its history clear, let's look at what actually happened that day. The rocket after liftoff accelerated smoothly and was going in its intended flight path. For rockets with no pilot on board, to follow such a precise path, it uses an onboard flight control system (FCS) and inertial reference system (SRI). Inertial reference system uses laser gyros and accelerometers to find the altitude, angle, and velocity of the rocket in real time, and uses a computer to transfer the data and run the code. This data is then fetched into the flight control system, which makes the required accelerations to follow the correct path. To make the system more reliable, two SRIs were used to back up whenever necessary. This arrangement worked fine until the 36th second, but at that minute, internal software bug caused the main SRI to shut down. Since the backup SRI was also running the same code, it also encoded the same minute bug and crashed. Both crashed SRIs didn't have any exception handling. In sense, didn't know what to do in such situation. So like any computer which does not know what to do in case of an error, they simply send the diagnostic data to the main flight control system. FCS, which heavily relied on SRI to make correct accelerations, misunderstood this diagnostic message as real flight data. For flight control's order, the decoded data showed it had deviated from the course by a very large margin, and to correct that, the flight control rotated the rocket into an angle of attack of more than 20 degrees. This created high aerodynamic forces which started ripping the boosters. This triggered the self-destruct mechanism, and the rocket was exploded at a height of 4000 meters. So, what was this minute internal software bug? Even though the development of Ariane 5 took around a decade, it shared some hardware and code for its SRI from its predecessor Ariane 4. This was done following a good coding practice, that is, reuse code whenever possible so that it doesn't break other code. Also, this is an accepted coding practice at the time. So while doing so, one small piece of code in the previous program was also kept. This code would normally run for 50 seconds after T plus 3 seconds after launch. It was used for alignment of elements in SRI. After liftoff, this piece of code is not required. Since Ariane 5 used a base station for such function, it didn't require this code necessarily. But they kept it anyway. Again, according to good coding practice. Don't remove code unless even though not required to make sure it doesn't break anything else. Inside, this code used to convert 64-bit floating point numbers to 16-bit integers for horizontal bias velocity measurement of SRI. It sounds a bit complicated, let me break it down for you. Floats are numbers which can store numbers ranging from 0 to a very large value which is greater than speed of light. Whereas, signed integers are numbers which can store value ranging from minus 32,000 to plus 32,000. So when the code tried to fit in a very large number inside a small space, the value overflowed its space, which triggered the system to shut down due to error. This function worked perfectly with all the many successful launches of Ariane 4. So they thought it won't be of any problem to Ariane 5 also. But there was one big problem. For Ariane 5, it was well within the signed integer limits, but Ariane 5 followed a different path and had very high acceleration. So when the value of horizontal BIOS velocity crossed the 32,000 limit, the code simply sent a diagnostic message to flight control and shut down. The same problem caused the backup SRIs to shut down after 72 milliseconds just after the first. And in just 3 seconds, the rocket killed itself above 4000 meters. Even after decades of development and billions poured, how did such a small software bug cause this disaster? This raises a very important question. Was this disaster avoidable? After the crash, an inquiry committee was formed to find the actual cause and possible changes that could have averted this disaster. They found several ways how this disaster could be averted. The same piece of code converted 7 such 64-bit floating point numbers to 16-bit integers, and 4 of them were coded so that they could handle such errors. The other 3 were left out unprotected. If all of them were protected, then such disaster would have never occurred. Also, exception handling should be more specific rather than default shutdown of the system when it encounters an error. Also, data fed into flight control system should be checked and real-time flight data should be transferred safely with validation. After learning from these mistakes, ESA went on to build another Ariane 5 rocket which launched successfully, and from then on it is one of the standard vehicles for space exploration. But still, this disaster pushed various research projects to be delayed and caused loss for humanity. So next time when you see a bug, remember there were really big bugs before yours. Thank you.